Today we will be looking at some of the items that are used in the production of reinforced concrete elements. One of the main constituents of concrete is coarse aggregate, commonly called gravel. The gravel should preferably be cubical or approximately cubical. Flaky or misshapen gravel should be avoided, especially for pumped concrete. Another main constituent of concrete is fine aggregate, commonly called sand, and the sand should be well graded with a range of particle sizes. The main bonding agent or cementing agent in concrete is cement, a fine powder that when water is added undergoes a chemical reaction called hydration. And hydration involves the development of long crystals that entangle the coarse and fine aggregate, resulting in a very, very dense matrix closely resembling rock. Cement is sometimes called hydraulic cement because it won't react without the presence of water. The water used in the production of concrete needs to be potable water. Care needs to be taken with a proportion of chlorides and other salts, otherwise the embedded reinforcement will tend to corrode. Today we're tending to use a wide range of recycled material that also has cementitious properties, sometimes called supplementary cementitious material. So most of these powders today are blended cements as opposed to ordinary Portland cement. Some of the supplementary cementitious material include slag, silica fume and fly ash. A variety of test cylinders are shown here using different types of coarse aggregate. It's important to note that the strength and hardness of the gravel plays a very big role in the strength of the concrete as a whole. Concrete has a range of properties and will proportion the various constituents according to the desired property. More cement will generally make the concrete stronger, so if we want a high strength concrete, the proportion or percentage of cement will be increased. Adding silica fume in the blended cement will tend to increase its rebound properties, making it suitable for shotcrete, and it will also make it less pervious to water, so it becomes more watertight and also improve its strength. Having too much water will tend to make the concrete shrink, so a low shrink concrete will have a small water to cement ratio. To increase the workability so the concrete has a greater slump, can be more easily pumped and placed and compacted around the reinforcement, we unfortunately will need to increase the water to cement ratio, making the concrete runnier. But runny or more workable concrete also tends to have reduced strength and increased cracking due to shrinkage. So to get around the dilemma of maintaining strength and minimizing shrinkage cracks, we can replace part of the water with a water reducing agent or a plasticizer that will lubricate the sand and gravel particles and achieve a more workable concrete while having a very low water to cement ratio. So with a water cement ratio of as low as 0.4, by adding a small dose of plasticizer, we can still maintain strength and minimize cracking. Without the reinforcement, the concrete is called plain concrete and is weak in tension. With the presence of reinforcement of any sort, the concrete is a composite material called reinforced concrete. The action of the reinforcement in improving its flexural capacity is not unlike this model with a rubber band being placed to cross the cracks. In order for those cracks to open, they will now have to stretch the rubber band, which of course in resisting the cracking gives it extra capacity. Steel or nylon fibres can also be added to the concrete mix to improve its capacity and tension. The ends of the steel fibres are hooked, as can be seen here, and this improves its ability to lock into either side of the crack and improve its resistance to being stretched and pulled through. Plain concrete can be reinforced either with deformed bars, welded mesh, sometimes called fabric, or with fibres. Reinforced concrete may also include ligatures or fitments, and to these ligatures or fitments the deformed bars are usually tied using annealed wire. The ligatures or fitments allow the main bars to be correctly placed in between the formwork, but they also improve a beam's shear capacity, because in the attempt of the bottom part of a beam tending to shear away from the top half, it needs to stretch these fitments that are placed at close centres. Hence, these closely placed fitments will improve a beam's shear capacity. The reinforcement tends to corrode, so to provide sufficient concrete cover to avoid corrosion, we have a variety of plastic chairs or concrete blocks that offset the bars or the reinforcement from the edge of the concrete. In the case of columns, we can use a different type of plastic chair to offset the reinforcement from the edges of the formwork. Ordinary reinforced concrete uses reinforcement that is passive in the sense that it's under no stress until loads are applied. This is different to pre-stressed concrete, which uses a different type of reinforcement, much like wire rope. And this wire rope is normally included within a sheath or duct that has many of these strands added together. The action of pre-stress can be understood by examining this model of a concrete beam or slab. When a load is added to the beam, it results in bending with tension cracks opening up in the bottom face of the beam. We're going to use a rubber band to represent the action of pre-stress. If pre-stress is applied to a concrete beam or slab, it tends to compress the beam or slab and close any cracks. And if this pre-stress were to be placed in the bottom of the beam or slab, it will tend to oppose the action of the load and reduce the cracking, as can be seen again by this model. So by placing it in the bottom of the slab, it will tend to bend it upwards, resisting and opposing the tendency of the beam or slab to bend downwards due to the load. There is some confusion between the terms screeding and floating. If we imagine that this represents formwork containing wet concrete, screeding involves using a straight edge to strike the surface of the concrete level with the form. The process will leave a surface full of imperfections and will need further treatment to densify and smoothen it out. In order to remove the imperfections and densify the surface of the concrete, we need to now pass over that surface with a mechanical or handheld float, and whether it be steel or timber, a float will densify the surface, embed the gravel and reduce any imperfections.